So I want to consider the use of Venn diagrams to illustrate counterexamples to quantify to arguments involving quantification. We have been using Venn diagrams to illustrate how to capture the notions of validity, and make it intuitive when the premises guarantee the conclusion, but through the geometrical relations between the sets that are represented as circles in the Venn diagram. So now what I want to do right now is just consider those cases of arguments which are invalid. So just give a couple of examples. Right. So so let's just start out by suggesting an argument which is invalid, right? So the following argument is an invalid argument. Some well, this is an argument which is valid. Sorry, invalid, but it is obviously invalid. So, for example, you could use this argument to actually illustrate how you can have how any argument having this form could have true premises and a false conclusion. But anyway, I think I just went over these two. Just came up with the first argument that I thought of, but I want to actually use an argument which is not as easy to judge as this one. So this argument here, argument A, obviously invalid in the sense that, as I mentioned, obvious true premises and obvious false conclusion. But let's do an argument of the same form as this one, which is more difficult to judge. So right, so if you notice this argument, it has the same logical form as the argument A above. We will display it in a second, but I think it's intuitive. So let's just call it argument B. And then we mentioned that in order to evaluate, using Venn diagrams, one of the first steps is just to judge the logical form of the argument. Translate all property or predicate expression just adjectives, etc. into schematic letters. But leave logical words unchanged. Then remember the logical words. Is we have of two types, right? We have propositional ones, which are and, or, if then, or implies, if and only if, not, and quantifiers. Such as all and some. Then having done that, translate that new expression to its most logically explicit form. So the example we used last time was when we translated all A's are B's into X is an A, then X is a B. So we already know how to translate the all quantifier, right, into something which actually looks like propositional logic, conditional type of sentence. Then here's a new translation. So expressions of this form are going to be translated as there exists an X such that X is an A and X is a B. Basically, the idea here is that when we're using some A or B, part of the logical content of that expression is to say that there's at least one A which happens to be a B, right? So basically that A and B, the intersection of A and B is not empty. So that's basically what we're going to be understanding by the claim that some A's are B's. So some A's are B's is true if there's at least one A which is a B. I mean, there could be more, of course, right? There could be many A's which are B's. There could maybe all A's could be B's, but it's going to be true that some A's are B's if there's just at least one X such that it is an A and it is a B. Okay. So here, just as long as there's one X which is both A and B, it's going to be true that there exists an X, or there's an X such that X is an A and X is a B. And that's going to make it true that some A are B. There could be more than one. In fact, every A will be a B. But just as long as there's one, some A or B is true. Okay, so that's the condition that must be satisfied in order for it to be true that some A or B. Just as long as there's one X, which is both an A and a B, right? So in the intersection of both, according to our set theoretic definition. Then once you have the translation, just draw a Venn diagram which captures the logical relations between sets according to our definitions. So what set theoretic definitions have we even? Well, we have defined union, intersection, subset, complement, etc. All of these, you know how, can be represented by Venn diagrams. So now consider, for example, just here, let me here just remember something that we showed last time. So suppose that I have something of the form all A's are B's, all A are B, and all B are C. Therefore, all A are C. We know that this is translated as if X is an A, then X is a B. If X is A, then X is B. And if X is B, then X is C. Therefore, X is A, and X is C. So that's a translation of the original argument. The original, so we can have an argument of the form all A's are B's, such as, you know, all cats are mammals, etc., etc. That we translate all cats are mammals to all A are B, all B are C. That this is just for the, you know, the examples that we looked previously to. Not this example today, but the ones we have discussed before. And these were to show validity, right? Not so much invalidity, not that the argument was such that the premises could be true and the conclusion false, but that if the premises are true, then the conclusion must be true. And the way in which we did this is by noticing that once we start drawing according to the instructions. So, for example, we draw the disease, which, you know, include everything that's the largest set, and we know that the B's are inside this, and the A's in turn are inside this, right? So let this be A, let this be B, and let this one be C, right? So we know that all A's are B's. That's satisfied here because if something, for example, let's put it here. If this is X, if X is in A, then X is in B. It's this region is included in this one, so that's true. And we know that all B's are C's, so that if X is in B, then X is in C. This is true here as well. And we know that this is a diagram for this sort of argument, right? But also notice that there's no other possible way in which we could draw a diagram like this. I mean, obviously we could make the circles a bit longer, etc. But in any possible way in which we draw this diagram, the A's will be included in the B's, and the B's will be included in the C's, because that's just the instructions that the argument is telling us through the premises, right? So premise one, everything that's an A is also a B, so the A's must be included in the B's. Everything that's a B is also a C, so the B's are included in the C's. So all of that's there. We know that relation, when we represent arguments like this through a Venn diagram, that relation has to be preserved. So all Venn diagrams are going to have that characteristic, right? All Venn diagrams of that argument are going to have that characteristic. That's one reason why we said last time that we don't need more than one Venn diagram for this type of argument. Once we have drawn this Venn diagram, this Venn diagram is the Venn diagram for all arguments of this sort. And it shows that every argument that has this form is logically valid, because it's not possible for the premises to be true. And then for those properties, which are represented as sets, as circles, not to be included within each other, right? So so this is valid, right? A valid argument, and it's always valid, always. As I mentioned, if an argument is valid, then every argument of the same form is also valid. That should be illustrated by the diagram, such as in this case, that the necessity of the inclusion is illustrated here. However, if an argument is invalid, if an argument is invalid, that means it will never be valid. It cannot possibly ever be valid. That argument with that logical form is never going to be valid, right? So it means that if an argument is invalid, then every argument with the same logical form is also invalid. So that should also be clear from the Venn diagram here. So notice the argument here, right? Argument B. So so let me just quickly illustrate this with a Venn diagram. Then we notice that the first premise, some minors are parents. Second premise are some parts are kind, and conclusion, therefore, some minors are kind. So let's just conclusion is, therefore, minors are kind, right? So, and I mentioned that this argument B, was a little bit more difficult to diagnose, because if you notice, the premises are true. I mean, some minors are certainly parents, and some parents are kind, definitely true. And the conclusion is also true. Therefore, some minors are kind. So because notice that it just requires that there's, in order for there to be the case that some parents are kind, there just needs to be one kind parent. I'm sure many of you have kind parents. There just needs to be, in order for some minors to be parents, there just needs to be one minor which is a parent. Sure, I'm sure that's true. It's also true that there's at least one minor which is kind. So that's enough for the claim that some minors are kind. That's enough for it to be true. So the premises are true, the conclusion is true. However, we have mentioned many times that you can have a deductively valid argument with false premises and false conclusion, with true premises and true conclusion, and you can, and with false premises and true conclusion as well. And the only instance in which your argument is going to be invalid is the case in which you have an argument that has true premises and false conclusion, right? So that's the only case in which the argument, in which an argument is going to turn out to be invalid. If it's possible for the premises to be true and the conclusion false. So you cannot have, the point is you cannot have a combination in an argument which is valid such that the premises are true and the conclusion false, right? But we have also mentioned that given that for an argument, the idea of validity of an argument does not mean that the premises and the conclusion must be true. As I just mentioned, you can have an argument which is valid where both premises and conclusion is false, and all sorts of combinations. So the idea is just that if the premises were true, the conclusion will be true, right? And then the point here is, how do we evaluate that for this sort of argument, right? And then the first technique that I showed you is the technique of constructing a counterexample, an argument that has the same logical form as the original argument, but where the premises are obviously true and the conclusion obviously false. That's not going to be possible if the argument is valid. But there's a more general way of doing so, which is through the use of Venn diagrams. So let's just first translate this into according to our instructions. So let's just, what are the properties involved here? The property of being a minor, let's represent that by the letter A. The property of being a parent, represent that by the letter B. And then the property of being kind, let's represent that by the letter C. And then the first translation is just going to be some A are B, some B are C. Therefore, some A are C. Because we leave the logical words alone, right? In our first translation, such as some and all, etc., right? And then we do the final translation, which is supposed to be completely explicit. And then we have to translate the quantifiers. So we already said how we are going to translate some. So there is an X such that X is an A, X is A, and X is B. So that's premise 1. Premise 2, there is an X such that x is b and x is c. So again, when I'm saying that some a are b, all I'm saying is that there is something, there is an x, such that x is an a and x is a b. When I'm saying that some b are c, all I'm saying is that there is something, an x, such that x is a b and x is a c. All right. And the same for some a are c. So all of these are translated in the exact same way, right? There is an x such that x is an a and x is c. So there we have it. And then notice here, there's an x here. That's all that part is saying is that there's an element in the set, a point in the Venn diagram. Remember that properties in the Venn diagram are represented by circles. And members sets are represented by points in the diagram. Right, so we had mentioned that before. So all that this part says here is that there is an x, so an element of the domain of the sets that we're going to be represented. So what this means is there is a point included in the circles of the Venn diagram. So we just have to notice what the next part of the expression here is telling us. So for example, this part here, right? This part here. So it's telling us, if you notice that x, that point in the Venn diagram, is A and is B, right? So this part here, the and, is really important. Notice that it is replicated in all premises. So in the end, what we're going to have is just an element of those sets, which is in the intersection, which is overlapping them both. We know that it exists because the claim is there exists. That's what the premises are telling us, that there is an x such that, etc. So so let's first draw the a's and the b's. We know that they overlap because there is an x in both. However, we don't know anything else than that. We know that We know that X overlaps A and B, and that X overlaps B and C, right? How do we know that? Because it's telling us again here, there is an X, and it's telling us that it is in A and in B, and it's telling us that it is in B and in C. And we know that we have our definition of intersection. That's just going to be the set of all X such that X is in A and X is in B. So exactly what we need, right? Just exactly what we need. So that's just the intersection. And we know that this intersection is not empty. We know that there's something in intersection. That's what premise one says. So premise one, there's something in intersection of A and B. Premise two, there's something in intersection of B and C. But notice that's all that the premises are telling us. That's it. It's not telling us that all A's are B's. It's not telling us that all B's are C's. It's just telling us that there's at least one thing which is both an A and a B, and there's at least one thing that is both a B and a C. And I guess you can already see what the issue here is, right? We don't have any reason to suppose that that X is the same X. There's nothing in the premises which guarantees that, nothing at all. So we should just draw the diagram with the information we have. We shouldn't add anything else to that. So the information that we have just says that there's something in the intersection of A and B. So this is a horrible diagram. So there's something here. And then we also know that there's something in the intersection of B and C. That's all it says, right? So this should satisfy that instruction. Notice that this diagram exactly is drawn according to what the premises and the conclusion is what the premises are saying. Not the conclusion. I'm sorry about that. Just follow the instructions in the premises, right? And then the premises, the first premise tells us there's an X such that X is in A and X is in B. Yeah, there's some overlap. We don't know how much. We just know there's overlap. So since that's all we know, this is how we draw it. We cannot guarantee anything else from the premises. And the premise two says that there's also something overlapping B and C. Again, that's all we know. So given that information, so let's just, so this is A, this is B, and this is C. So given that information, we cannot actually guarantee, I mean, it's pretty evident from the geometry that there's no guarantee that that if the premises are true, that if there's an X which is such that it's A and B, and if there's an X which is B and C, there's no guarantee that there's going to be an X which is A and C. Yeah, I mean just like in the old case that we just did last time, and which I just represented, in this page here, we just follow the instructions in the premises. But following the instructions for this argument, all A are B, all A are B, all B are C, therefore all A are C, that forces us to draw a certain kind of diagram in which these sets are always included. The A's are always included in the B's and the B's in the C's. So we know that argument is going to be valid because that geometrical relation is always going to be preserved. And again, we just followed those instructions. We didn't add anything else, but that was enough. That was enough such that if we represented the premises, then the conclusion was automatically represented by the inclusion relationship. And in this case, we just, again, follow the instructions. We drew the relevant properties as sets according to the Venn diagram instruction. It just told us that there was something in the intersection of A and B and of B and C, but that wasn't enough to guarantee that there was something in the intersection of A and C. So that if something is both A and B, and something is both B and C, it must therefore be the case that something is both A and C. And this was premise one. Premise two. The conclusion, right? So so the premises will not guarantee the conclusion. The truth of the premises, even assuming they are true, therefore the argument is invalid. And every argument having that form is also invalid. Right. Yeah, I think that should be sufficient for these sorts of examples. But yeah, so I will leave it for today. I will leave it here.